In analytics projects, having the appropriate sample size is important to allow us to infer some analysis onto our population. In previous modules, we had focused on confidence intervals around population means, proportions, differences between means, and differences between proportions. It's important that we have an appropriate sample size when we do these confidence intervals. And it's a function of three things. Number one is the data used. The variance of the data we have in our sample will affect the confidence interval. All of the formulas that we had shown with confidence interval are affected by standard error. If our error increases because of the sample, our confidence interval will be wider. The confidence level has a clear impact on the length because it's a constraining factor on the interval. A 99% confidence level will always be shorter than a 95 or 90% confidence level. And finally, the overall sample size. The more data you have, the more narrow the confidence level will be. And this is because increasing the data will increase the accuracy, because the variability will reduce. Our previous formulas had shown the form for the confidence intervals as a point estimate plus or minus some multiple times standard error. The right side of the plus minus indicates how much we want our confidence interval to span, at least in one direction, plus or minus. So if we want a confidence interval to be plus or minus 10, we would want the right side of that plus and minus to equal 10. And therefore, we can actually create the following equation. T multiple times the standard error, which is denoted here as the sample standard deviation divided by the square root of n, equals 10. We can then solve for n to get an appropriate sample size. So this is a way for us to determine how much of a sample we need based on an estimated standard deviation. So let's say we want to write this out and we want to have a confidence level of plus or minus some letter b. We would take our formula, the t multiple times the sample standard deviation divided by the square root of n equals b. Solving algebraically, we could do the following. We could change this to the t multiple times the sample standard deviation is equal to b times the square root of n. Further, divide both sides by b, and we end up with the square root of n is equal to the t multiple times sample standard deviation all over b. We can remove the square root by squaring both sides, and we end up with the following. N equals the t multiple times sample standard deviation over b, and take that whole quantity squared. Now you may notice that there's a problem because we don't have the sample size to know what the sample standard deviation is going to be. Since we don't have the sample, if we are given a population standard deviation, we can use that along with a z multiple. And recall that if we have the population standard deviation, we can use the z multiple because we don't have that extra variability that gets introduced if we have a sample standard deviation. So we can then rewrite the formula as follows, using the z multiple and the population standard deviation that we are given. So using the formula, if we wanted to obtain a confidence interval of plus or minus 0.4 with a confidence level of 95% and a population standard deviation of 1.693, we could do the following. We take our z multiple and we put in the confidence level of 0.95. Now remember, since this is two tails, we're going to divide the difference by 2 and we're going to make it 0.975. And this will give us 1.96. And our problem statement gave us a population standard deviation estimate of 1.693. So b being 0.4 from above, we can replace the values into the formula. And we get 1.96 times 1.693 divided by 0.4 and then square it. Solving for this, we end up with n equals 68.72. But since these are required samples, we can't really have a decimal, so we'll round it up to say we need 69 observations. Now this slide basically just takes the previous formulas for the confidence intervals and simply does the algebra to actually show you the formula to calculate the sample size for estimating a population mean, estimating a proportion, the sample size for estimating difference between population means, and the sample size for estimating differences between proportions.